And now in this lecture we will find out the radius of the small circle. In the drawing we have a semicircle, and inside the semicircle we have a circle, so the circle is inscribed by the semicircle. You know that side CD equals to 4 units, side DB equals to 4 units, and angle CDB equals to 90 degrees. It is a right angle, and we want to find out the radius of this small circle that is inscribed by the semicircle. Okay, so first of all we will do a construction. We will complete the semicircle to a circle. So we completed the semicircle to a circle, and we will extend side CD until it touches the circle. And we will define the touching point of the extended line segment CD with this circle as point E. So actually here we extended the straight line CD by a straight line, so actually CE is a straight line. And we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So this angle at point D and this side of the straight line CE at point D, the sum of the angles must be equal to 180 degrees. So which angles we have at point D on this side of the straight line CE? We have here 90 degrees, but plus angle EDB. So here 90 degrees plus angle EDB. In total, they must be equal, those two angles, EDB, 90 degrees plus angle EDB, in total they must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So we will subtract 90 degrees from this equation, and we get that angle EDB equals to 180 degrees minus 90 degrees, it is 90 degrees. Okay, so this angle is a right angle, it is equal to 90 degrees. And actually, side CD must be equal to side DE by symmetry. Side CD, this side CD, must be equal to side DE, and those two sides, they are equal to each other, those two line segments are equal to each other by symmetry. I will explain what I mean that those two line segments are equal to each other by symmetry. First of all, the second semicircle that we constructed from the original semicircle is a mirror image of the original semicircle. Okay, the second semicircle, this semicircle is a mirror image of the original semicircle. That is to say, if you fold the two semicircles in such a way that we close them together, then they will overlap each other, they will be congruent to each other. Okay, and we know that this angle equals to 90 degrees. So here, actually, side D, point D, is a common point of the line segment EC and the line segment ED. And if we fold those two line segments in such a way, like this way, then they overlap each other, they will be congruent to each other. For that reason, point E will merge point C, and therefore, and we know that point D is a common point that belongs to both straight lines, therefore we'll get that DE will be equal to CD by symmetry. Point E will merge with point C if we fold those two semicircles like that, and for that reason, and we know that angle EDB equals to 90 degrees, so if we fold those two semicircles, then point E will merge with point C, and point D is a common point, that is to say, CD will be equal to DE by symmetry. Okay? So CD equals to DE by symmetry, but it is given us the question that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE. We will derive that DE is also equals to 3 units. DE equals to 3 units. Okay? Here DE is also equals to 3 units. And we actually have a rule, I call it rule number 1. According to rule number 1, if two chords intersect with each other outside the circle, then the following equation is true. I write it down. If two chords intersect with each other inside the circle, then the following equation is true. So here we have a circle. We have a circle. Inside this circle we have two chords that intersect with each other. So the first chord is called this is chord AB that intersects with chord CD. This is chord CD. So chord AB, the red chord, intersects with CD, the blue chord, and the intersection points is at point O. So in this case, the following equation is true, that AO times OB equals to CO times OD. Okay? I'll repeat again. If we have this circle and we have two chords that intersect with each other inside this circle, that is to say, chord AB intersects with chord CD at point O. Point O is the intersection point of those two chords. Then according to rule number 1, AO times OB equals to CO times OD. We can actually implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB that intersects with chord CE at point D. Point D is the intersection point of those two chords. I write it down. In our original drawing, we know that chord CE, this chord CE, intersects with chord AB at point D. Point D is the intersection point of chord AB with chord CE. I repeat again, in our original drawing, chord CE intersects with chord AB at point D. Point D is the intersection point of chord CE with chord AB. Therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. Okay? So according to rule number 1, we get that AD times DB equals to CD times DE. So AD is the missing line segment, so we leave it as it is. AD times DB. DB, it is given us the question that DB equals to 4 units. Here, DB equals to 4 units, so we substitute DB by 4. CD is 3 units, and we already found out that DE is also equal to 3 units. So in conclusion, we found out that AD times 4 equals to 3 times 3. That is to say, 4 times AD equals to 3 times 3 is 9. So 4 times AD equals to 9. We divide this equation by 4 and we get that AD, the missing line segment, equals to 9 over 4 units. So we found out here the missing line segment AD equals to 9 over 4 units. Okay? So AB is the diameter of the circle and also the diameter of the both quarters, and also the diameter of both semicircles, of course. So the diameter is twice as long as the radius. So we divide the diameter AB to 2 in order to get the radius of the big circle. That is also the radius of the semicircles. Okay, so R will be equal to, so we'll define as capital R. Capital R is defined as the radius of the circle, that is also the radius of the semicircles. So capital R will be equal to AB, that is the diameter AB. If we divide the diameter by 2, we'll get the radius, that is capital R. So I repeat again, that the radius of the circle and also the radius of the semicircles, it is equal to AB, that is the diameter, over 2. What is the length of AB? AB equals to AD plus DB. AB equals to AD plus DB over 2. So here AD equals to 4 over 9, and it is given us the question that DB equals to 4 units, all divided by 2. And here we'll multiply 4 by 9 and we will divide it, it is actually 9 over 4. AD equals to 9 over 4. Here AD equals to 9 over 4. And DB equals to 4 units according to what is given us the question. So here we multiply 4 by 4 and then we divide it by 4 in order to have a common factor with 9 over 4. So we get here that is 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25 over 4 times 2. 4 times 2 is 8, so in the denominator we have 8. So in conclusion, we found out that the radius of the semicircles and also the radius of the big circle, it is equal to 25 over 8 units. Okay? The radius of the big circle and also the radius of the semicircles, they are equal to 25 over 8 units. In the next step, we will define the center of the circle and also the center of the semicircles as point P. And here we will define the center of the small circle as point Q. Okay? Here, from the center of the small circle, that is to say from point Q, we will draw the radius to the point of tangency of tangent DB with this small circle. So we will define the point of tangency of tangent DB with this small circle as point M. QM is the radius of the small circle because of the fact that line segment QM starts from point Q, that is the center of the small circle, and ends at point M, that is the point on the circle itself. And this is exactly the definition of a radius. So QM equals to R. So if the radius QM is drawn to the point of tendency, and because of that fact that the radius QMR is drawn to the point of tendency, that is point M, then tangent DB will be perpendicular to radius MQ. Again, DB is perpendicular to MQ. Okay? Whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent DB perpendicular to the radius MQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from the center of the small circle, we will draw the radius to the point of tangency. Here, this is the radius. The radius of the small circle is drawn to the point of tendency. That is to say, it is drawn to this point. We define this point as point L. Point L is the point of tendency of tangent CD with this small circle. So we have the radius QL that is drawn to the point of tangency of tangent CD with this small circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius LQ. Again, CD is perpendicular to LQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. According to the rule that I mentioned, that a tangent to a circle is perpendicular to the radius drawn to the point of tendency. Whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. CD perpendicular to LQ, that is to say, this angle equals 90 degrees, and this angle also equals to 90 degrees. So we will focus on quadrilateral LQDM. This quadrilateral LQDM in quadrilateral LQDM, we have 1, 2, 3 right angles. Again, in this quadrilateral LQDM, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle inside quadrilateral LQM, D, that is angle LQM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Again, in quadrilateral LQDM, the sum of the angles must be equal to 360 degrees. That is to say, the sum of 3 angles is 270 degrees, 3 right angles, plus the size of the 4th angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we get that the missing angle LQM is equal to 360 degrees minus 270 degrees, it is 90 degrees. Okay? So the missing angle LQM, it is a right angle. This is a right angle. Actually, quadrilateral LQDM, this quadrilateral has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral LQDM as a rectangle. LQDM is a rectangle. Okay, quadrilateral LQDM is a rectangle because of the fact that it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, LQ equals to DM. In rectangle LQDM, LQ equals to DM. LQ equals to DM according to the rule that the opposite sides of a rectangle are equal to each other. Therefore, LQ equals to DM. But we know that LQ is the radius of the small circle. We can write here that LQ equals to small r. And from this equation, r equals to LQ equals to DM, we will derive that DM is also equals to r, small r. DM equals to small r, that is the radius of the small circle. So here we can write down that DM equals to r, that is the radius of this small circle. Okay? And what is the length of DP? For the drawing, it is very easy to see that the length of line segment DP is equal to dB minus PB. dB minus PB. dP equals to dB minus PB. Repeat again. dP equals to dB minus PB. dB equals to 4 units according to what is given as the question. dB equals to 4 units. So it is 4 minus PB. And PB is the radius of the big circle according to our definition. Why? Because line segment PB starts from point P, that is the center of the semicircle, and also the center of the circle itself, and ends at point B, that is the point on the circle itself, or the semicircle itself also. And this is exactly the definition of a radius. So PB equals to capital R. So in conclusion, we found out that dP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8. So we can substitute R by 25 over 8. So dP equals to 4 minus R is 25 over 8, according to what we have already found out. And here we will multiply 4 by 8 and we will divide it by 8 in order to have a common factor with 25 over 8. And we get that dP equals to 4 times 8 is 32 minus 25 over 8. 32 minus 25 is 7. So in conclusion, we found out that dP equals to 7 over 8 units. Okay, dP equals to 7 over 8 units. We can write here that dP equals to 7 over 8 units. In the next step, we will we'll draw the radius from point P until it touches the point of tendency of the small circle with the big circle. Here we define the point of tendency of the two circles as point S. Actually, PS is the radius of the circle itself, that is to say it is equal to 25/8. But the point here that the point here is that PS, that is the radius of the big circle, must pass through point Q. Or we have actually a rule, will be rule number 2. That whenever two circles have an internal length between them, that is to say they are touching each other internally, then the straight line that joins together, that connects the centers of the two circles, that is to say in this case is PQ, because P is the center of the big circle and Q is the center of the small circle. This straight line, the straight line PQ, must pass through the point of tendency. That is to say from the point, for the launch point of those two circles. Here point S is the launch point, and here PQ must pass through point S. Okay, so maybe I write it down. If two circles have an internal launch between them, that is to say they are touching each other internally, then the straight line that connects the centers of the two circles that is to say, in this case is PQ, write it in brackets, must pass for the launch point, that is the point of tendency. In this case, it is point S. Okay, so I'll read rule number 2 again. If two circles have an internal launch between them, then the straight line that connects the centers of the two circles, that is to say, in this case it is PQ, must pass through the launch point, must pass from point S, that is the point of tendency of the small circle with the big circle. Okay? That is also called the launch point. The launch point of the point of tendency of the small circle with the big circle. For that reason, so PQ must pass through point S. Therefore, PQS is one straight line. Because if we extend PQ by straight line, we must arrive to point S. So if we extended the straight line PQ by straight line, so PS is also a straight line. And PS is the radius of the big circle. Okay, PS equals to R. You can write here also that PS equals to capital R. So PS minus QS equals to PQ. PQ equals to PS minus QS. Repeat again, PQ equals to PS minus QS. So PQ equals to PS, that is capital R, it is the radius, PS is the radius of the big circle because of the fact that it starts from the center of the big circle, that is to say from point B, and ends at point S, that is the point on the circle itself. And this is exactly the definition of a radius. So PS is the radius of the big circle, that is to say it is equal to capital R, and QS is the radius of the small circle, that is to say it is equal to small r. Why QS is the radius of the small circle? Because of the fact that line segment QS starts from the center of the small circle, that is to say from point Q, and ends at point S, that is a point on the small circle itself. And this is exactly the definition of a radius. So QS equals to small r. So in conclusion, PQ equals to capital R minus small r. So PQ equals to capital R, that is 25 over 8, minus small r. So you can write here that PQ equals to 25 over 8 minus r. Okay, PQ equals to 25 over 8 minus r. And what is the length of line segment PM? The length of line segment PM, it will be equal to PD DB minus, it is equal to DM minus DP. PM equals to DM minus DP. I'll repeat again. PM equals to DM minus DP. Again, DM minus DP equals to PM. It is very easy to see from the drawing. PM equals to DM minus DP. DM is the radius of the small circle, that is to say it is equal to small r. DM equals to small r minus dp. We have already found out that dp equals to 7/8, 7 over 8, or 7/8. So in conclusion, we found out that PM equals to R minus 7 over 8. You can write here that PM equals to R minus 7 over 8. Now we can implement the Pythagoras theorem on the green right triangle, triangle PQM. So I'll copy the right green triangle, triangle PQM in a new page, and we will implement the Pythagoras theorem in the right triangle PQM. You can see that the only missing variable in this right triangle is R, and in this way we'll find out the value of R. That is the thing that we want to find out in this question, to find out the radius of the small circle that is actually equal to small r. So I'll copy the right triangle PMQ in a new page. We know that QM is the radius of the small circle, that is to say it is equal to small r. PM, we just right now found out that PM equals to r minus 7/8. And we already found out that the hypotenuse PQ equals to 25/8 minus r. So this is the right triangle QPM that I copied from the original drawing. So in the right triangle QPM by PT, that is by Pythagoras theorem, abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this will be equation number 1. According to equation number 1, we will get that the square of the hypotenuse is PQ, therefore the square of the hypotenuse is PQ square, and it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to PM square plus QM square. Okay? Repeat again, according to the Pythagoras theorem and the right triangle PQM, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say PQ square equals to PM square plus QM square. PQ equals to 25/8 minus r, so therefore PQ square will be equal to 25/8 minus r square, and it is equal to PM square. PM equals to r minus 7/8. Therefore, PM square will be equal to r minus 7/8 square plus QM. QM equals to r, so QM square will be equal to r square. Here we will open the brackets on both sides of this equation, equation number 1, and we will get that according to equation number 1, (25 minus r square). It is equal to 25/8 square, that is 25 square is 625, over 8 square is 64. So in conclusion, 25/8 square is 625 over 64. And so it is a minus b squared, it is equal to a squared plus b squared plus r squared, minus 2 times ab, that is minus 2 times 25/8 times r. We finished with this side of equation number 1. Now we will go to the other side of this equation number 1, and we'll open the brackets here. R minus 7/8 squared, r minus 7/8 squared equals to r squared plus 7/8 squared is 49/64, minus 2 times r times 7/8 plus r squared. So here we have r squared on both sides of the equation, so r squared will get cancelled. And in this side of equation number 1, what is left after we cancel r squared is 625/64 minus, here we divide both the numerator and the denominator of this expression by 2. 2/2 is 1, so here we will have 25r, and 8/2 is 4. So in conclusion, this expression, after we divide it by 2, both the numerator and the denominator, it is equal to 25r/4, with minus 25r/4. In the other side of the equation, we have 49/64 minus, here we will divide this expression 2r times 7 over 8, both the numerator and the denominator by 2. So minus 2r times 7 over 2 is minus 7r. And here we have in the denominator 8, so 8 over 2 is 4. So in conclusion, this expression 2r times 7 over 8 is equal to minus 7r over 4 plus r squared. Here we will multiply this equation by 64 in order to get rid from the denominator that is actually two expressions have denominator that is equal to 64. So here 64 over 64 is 1, so what is left here is 625 minus 64 over 4 is minus 16 times 25r, and in the other side of the equation we have this expression. So here 64 over 64 is 1, so we left only with 49, and here we have minus 4r, or minus 64 over 4 is minus 16 times 7r, and here 64 times r squared is 64r squared. Okay, so here in conclusion, according to equation number 1, we found out that we have 64r squared according to equation number 1, 64r squared we will here actually minus 16 times 7r is minus 112r plus 49, that is equal to 625 minus 16 times 25r is minus 400r. So in conclusion, we found out that according to equation number 1, 64r squared minus 1200r plus 49, of course, here it is 49, equals to 625 minus 400r. We'll add 400r to this equation, equation number 1, and we'll get that according to equation number 1, we have 64r squared 400r minus 112r is plus 288r plus 49 equals to 625. We will subtract 625 from this equation, equation number 1, and we get that according to equation number 1, 64r squared plus 288r, here 49 minus 625 is equals to minus 576. I'll check it. $49 minus 576. Actually it is 49 minus 625. 49 minus 625, it is indeed equals to minus 576. So in conclusion, we have the quadratic equation that 64r squared plus 288r minus 576 equals to 0. We will divide this equation by 32. 64 over 32 is 2. So this expression equals to in total to 2r squared. 288 over 32 is 9. So this expression equals to in total to 9r. And minus 576 over 32 is minus 18. Okay. So we have here a quadratic equation. The missing variable here in this quadratic equation, the variable that we are looking for is r, the radius of the small circle. So x equals to r. The coefficient a equals to 2. This quadratic equation, the coefficient b equals to 9. And the coefficient c equals to minus 18. And the general formula for solving out a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So in our specific quadratic equation, x equals to r. So we substitute x by r, and it is equals to minus b. b equals to 9, so minus b is minus 9. Plus minus square root of b squared. b is 9, so b squared is 9 squared, it is 81. Minus 4 times a is 2. c is minus 18. Over 2a. a is 2, so 2 times 2 is 4. So in the denominator we have 4. So r actually equals to minus 9 plus minus. Inside the root we have minus 18 times 2 is minus 36. Minus 36 times minus 4 is plus 144. So in conclusion, inside the root we have 81 plus 144, all divided by 4. Here r equals to minus 9 plus minus. Inside the root we have 81 plus 144 is 225, all divided by 4. So here r equals to minus 9 plus minus the square root of 225 is 15, all divided by 4. So here we will have two solutions that are possible for r. The first solution for r is r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number of course, but because of the fact that r is the radius of the small circle, that is to say r is a length, because it is the length of the radius of the small circle. So r is a length, must be a positive number. That is to say, it can never be equal to -6. That is a negative number, so we cancel this solution. And we left only with the second solution. That is actually r equals to -9 plus 15 over 4. -9 plus 15 is 6, and 6 over 4, so r equals to 6 over 4. We will divide both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r equals to either 3 over 2 units, or we can present it as 1.5 units. And this is the answer to the question, that the radius of this small circle that is inscribed by the semicircle, it is equal to either 3 over 2 units, or we can present it also as 1.5 units. Okay, in the next step I will summarize the lecture. Okay. Actually, the question, we have a circle that is inscribed by a semicircle, and we want to find out the radius of the circle that is inscribed by the semicircle. Okay? So, first of all, we did a construction. We completed the semicircle to a circle. We also know that side CD equals to line segment CD equals to 4 units, and line segment DB equals to 4 units, and angle CDB equals to 90 degrees. So we did the construction. We completed the semicircle to a circle. And then we extended line segment CD by a straight line until it touches the circle at point E. Point E is the touching point of the extended CD and the circle. And actually here the new semicircle that we created by the construction is a mirror image of the original semicircle. I'll repeat again. The new semicircle that we created here, this semicircle is a mirror image of the original semicircle. And here we extended the straight line CE by a straight line, so the result must be a straight line. So we know that CE is a straight line, and we know that the sum of the angles from one side of a straight line is equal to 180 degrees. So at point D, at this side of the straight line CE, the sum of the angles must be equal to 180 degrees. So which angles we have at point D, at this side of CE? We have here 90 degrees and angle EDB. So according to the rule that I mentioned, 90 degrees plus angle ADB must be equal to 180 degrees in total. We subtracted 90 degrees from this equation and found out that the missing angle, EDB, this angle is a right angle. So we actually know that this is a right angle, and this semicircle is a mirror image of the original semicircle. Okay? And for that reason, we can say that CD equals to DE by symmetry, because of the fact that the semicircle that we created is a mirror image of the original semicircle, and angle EDB equals to 90 degrees, exactly as angle CEB that is also equals to, exactly as angle CDB that is also equal to 90 degrees, and the new semicircle that we created is a mirror image of the original semicircle. It means that here CD must be equal to DE because of the fact that here DE is the mirror image of CD. That is to say, the length of those two line segments must be equal to each other. They have different directions. Like when you look at the mirror, you see yourself in the opposite manner, exactly like this. DE is the opposite side of CE, but the length, because it is a mirror image, must be equal to CD. That is to say, CD that is ED that is a mirror image of CD must be equal to each other, because one is the mirror image of the other. And when you look at the mirror, you see yourself opposite, but your length doesn't change. Okay? So therefore, again, I repeat again that CD equals to DE by symmetry, and by note that CD equals to 3 units according to what is given as the equation. So from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Okay? In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. AO times OB equals to CO times OD. Again, so here we have chord AB that intersects with chord CD inside the circle at point O. Okay? Chord AB intersects with chord CD inside the circle at point O. Point O is the intersection point of chord AB with chord CD. Therefore, according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord CE intersects with chord AB at point D. Point D is the intersection point of chord AB with chord CE. I'll repeat again. In our original drawing, we have chord CE that intersects with chord AB at point D. Therefore, we get that according to rule number 1, that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. AD times DB equals to CD times DE according to rule number 1. AD is the missing line segment. DB equals to 4 units according to what is given us in the question. So here we can substitute DB by 4. It has given us the question that CD equals to 3 units, and we have already found out that DE is also equals to 3 units. So in conclusion, we found out that 4 times AD equals to 3 plus 3, to 3 times 3. That's to say 4 times AD equals to 3 times 3, that is 9. 4 times AD equals to 9. We divided this equation by 4 and found out that AD equals to 9 over 4. So here AD equals to 9 over 4. Now, we know that AB is the diameter of the semicircle and also the diameter of the circle itself. And the diameter of any circle or semicircle is twice as long as the radius. So we divide the diameter AB into 2. In this way we will find out the radius of the big circle or semicircle also, and we'll define the radius of the big circle and also the radius of the semicircle as capital R. Therefore we'll get that AB over 2 equals to capital R. Okay? Capital R, the radius of the big circle, equals to the diameter of the big circle, that is AB over 2. What is the value of the diameter AB? From the drawing it is easy to see that AB equals to AD plus DB. Again, AB equals to AD plus DB. AB equals to AD plus DB. We have already found out that AD equals to 9 over 4. Okay? According to rule number 1, we have already found out that AB equals to 9 over 4. And it is given us the question that DB equals to 4 units. So in conclusion, AB equals to 9 over 4 plus 4 over 2. It is actually R equals to 9 over 4 plus 4 over 2. Here we multiplied 4 by 4 and then we divided by 4 in order to have a common factor with 9 over 4. So here 4 times 4 is 16 plus 9 over 4 over 2. 9 plus 16 is 25. 25 over 4 over 2. So 2 moves to the denominator. So in conclusion, we found out that R equals to 25 times 25 over 4 times 2. 4 times 2 is 8. So in conclusion, we found out that the radius of the big circle, that is also the radius of the semicircles, it is equal to 25 over 8 units. So the radius of the big circle and also the radius of the semicircles, they are equal to 25 over 8 units. Okay? It is, of course, the same radius. Okay? The radius of the semicircle is also the radius of the circle itself. And it is equal to 25 over 8 units. Then we focus on quadrilateral LQPM. Here we joined, actually here P is the center, we defined P as the center of the circle and the semicircle itself, the big circle, and we defined Q as the center of the small circle. From the center of the small circle, we draw the radius to the point of tendency, that is to say, that is the point to point L, that is the point of tendency of tangent CD with this small circle. So whenever you have a radius that is drawn to the point of tendency, then the tangent CE will be perpendicular to the radius LQ. CE is perpendicular to LQ, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Likewise, from point Q, that is the center of the small circle, we draw a radius of the small circle that is drawn to the point of tendency, that is to say the radius QM, that is equal to small r according to our definition. It is drawn to the point of tendency, that is to say to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. DB is perpendicular to MQ, that is to say this angle equals to 90 degrees and this angle equals also to 90 degrees. So in quadrilateral LQDM we have 1, 2, 3 right angles, and this the fourth angle. So in quadrilateral LQDM, the sum of three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actual angle LQM. In total, the sum of those four angles inside quadrilateral LQDM must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? You subtracted 270 degrees from this equation and found out that the missing angle, the fourth angle, angle QM, equals to 360 degrees minus 270 degrees is 90 degrees. So the missing angle here, angle LQM, equals to 90 degrees. That is to say, in quadrilateral LQMD, we have four right angles. Any quadrilateral that has four right angles must be at least a rectangle. So we relate to quadrilateral LQDM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle LQDM, LQ must be equal to DM. In rectangle LQDM, LQ must be equal to DM according to the rule that the opposite sides of a rectangle are equal to each other. LQ must be equal to DM. Okay, LQ must be equal to DM. But we know that LQ is the radius of the small circle, that is to say it is equal to small r, it's the radius of the small circle. So I can write here that LQ equals to small r, it is the radius of the small circle, and from this equation r equals to LQ equals to MD, we will derive that MD is also equal to r. Here, Nice Math MD or DM, it is equal to r, that is the radius of the small circle. It is equal to small r, that is the radius of the small circle. Okay, then we found out the length of the small line segment DP. What is the length of DP? The length of DP equals to dB minus PB. Again, dB minus PB equals to dP. I'll repeat again. Here, dP equals to dB minus PB. Okay? dP equals to dB minus PB. It is given as the equation that dB equals to 4 units. Here, dB equals to 4 units. PB, it is the radius of the big circle. Why? Because P is the center of the big circle, and B is the point of the big circle itself. This is exactly the definition of a radius. So PB is the radius of the big circle, that is to say it is equal to capital R. Okay? PB equals to capital R. So in conclusion, we found out that dP equals to 4 minus capital R, that is to say dP equals to 4 minus capital R, and we have already found out that capital R equals to 25 over 8. So in conclusion, dP equals to 4 minus 25 over 8. Here we multiplied 4 by 8 and then we divided by 8 in order to have a common factor with 25 over 8. So 4 times 8 is 32, so here we have the denominator of 32 minus 25 over 8. 32 over 25 is 7, and in conclusion dP equals to 7 eighths. 7 eighths. Here dP equals to 7 eighths. Then I presented to you rule number 2. According to rule number 2, if two circles have an internal length between them, then the straight line that connects the centers of the two circles, in this case it is PQ, must pass through the launch point, that is point S. So I repeat on rule number 2 again. According to rule number 2, if two circles have an internal length between them, that is to say, if they are touching each other internally, like in this case, the small circle touches the big circle at point S. Therefore, those two circles have an internal length between them. Then the straight line that connects the two centers together is PQ, because P is the center of the big circle and Q is the center of the small circle. Therefore, line segment PQ, it is the straight line that connects the two centers. So according to rule number 2, this straight line PQ must pass from the launch point. That is to say, from point S, that is the launch point, that is the point of tendency of the small circle with the big circle. Again, the line segment PQ, that is the straight line that connects the two centers of the small circle with the big circle, must pass for the point of tendency of the two circles when you have an internal launch between those two circles. In this case, we have an internal launch between those two circles, that is to say they are touching each other internally at point S. Therefore, the straight line that connects the two centers together, that is PQ, must pass through the launch point, that is point S. So PQS must be one straight line, and indeed PQS is one straight line that is also the radius of the big circle. So here we know that PQS is one straight line, therefore PQ is the radius of the big circle, that is equal to capital R, while QS is the radius of the small circle, that is equal to small r. Okay? And then PQ, what is the length of PQ? PQ equals to PS minus QS. Again, PQ equals to PS minus QS. PS is the radius of the big circle. Why? Because it starts from the center of the big circle and ends at point S, that is the point of the big circle itself. This is exactly the definition of a radius. So PS equals to capital R, and SQ equals to small r. Why SQ equals to small r? Because point Q is the center of the small circle, and point S is a point on the small circle itself, and this is exactly the definition of a radius. That is to say, QS equals to the radius of the small circle, that is to say, it is equal to small r. So in conclusion, PQ, that is equal to PS minus QS, equals to capital R minus small r. Capital R equals to 25 over 8. We already found out that capital R equals to 25 over 8, and R is the missing line segment that we are looking for in this lecture. This is the line segment that we want to find out. So in conclusion, we found out that PQ equals to 25 over 8 minus R. PQ, this is also the hypotenuse of the green right triangle QPM, equals to 25 over 8 minus small r. Here QM, we already found out that QM equals to small r, that is the radius of the small circle. And what is the length of PM? Here PM equals to dm minus dp. Again, PM minus PD, PM minus PD equals to PM. Again, PD, the line segment PM, equals to dm. Here, dm minus dp equals to pm. Here, pm equals to dm minus dp. Again, pm equals to dm minus dp. Okay, so pm equals to dm, that is the radius of the small circle, that is to say it is equal to small r, minus dp. We have already found out that dp equals to 7/8. dp equals to 7/8. And now we implemented the Pythagoras theorem on the right triangle QPM. According to the Pythagoras theorem, PT is the equation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the square of the perpendiculars. That is to say, QP square equals to PM square plus QM square. Again, according to equation number 1, PQ square equals to PM square plus QM square. PQ equals to 25 over 8 minus R. So PQ square equals to 25 over 8 minus R square. And it is equal to PM square. PM equals to R minus 7 eighths. So PM square equals to R minus 7 eighths square plus QM square. QM equals to R, so QM square equals to R square. So here we open the brackets on both sides of this equation, equation number 1, and found out that according to equation number 1, 25 over 8 minus R square equals to 25 over 8 square, that is 625 over 64, plus R square, minus 225 over 8 times R. And it is equal to R minus 7 eighths square. R minus 7 eighths square equals to R square plus 7 eighths square, that is 49 over 64, minus 2 times R times 7 eighths plus R square. Here we have R square on both sides of the equation, so R square will get cancelled. And in this side of the equation we left only with 625 over 64. And here we divided both the numerator and the denominator of this expression by 2. So here 2 over 2 is 1, so in the numerator we left only with 25R. And in the denominator we have 8 over 2, that is 4. So in conclusion, this expression, after we divide it by 2, equals to 25R over 4, and it is equal to 49 over 64, and here we have 2R times 7 eighths. We divided both the numerator and the denominator of this expression by 2. 2 over 2 is 1, so in the numerator we have minus 7R, and in the denominator we have 8 over 2 is 4. So in conclusion, this expression equals to 7R minus 7R over 4 plus R square. Here we multiply this equation, equation number 1, by 64, and we got that 64 over 64 is 1, so we left only 625. And here 64 minus 64 over 4 is minus 16, so this expression equals to in total minus 16 times 25R. 64 over 64 is 1, so what is left from this expression is only 49. And we have here minus 64 over 4 is minus 16. So this expression in total equals to minus 16 times 7R. 64 times R square equals to 64R square. Okay. So here we have 64R square, and we have here actually we have in this side of the equation we have 64R square, and minus 16 times 7 is minus 112R. This expression equals to minus 112R plus 49. So in this side of the equation we have 64R square minus 112R plus 49. And in the other side of the equation we have 625 minus 16 times 25R equals to minus 100R. So in the other side of the equation we have 625 minus 400R. We added 400R to this equation, equation number 1, And we found out that according to equation number 1, 64r squared, here 100r minus 112r equals to 288r plus 49, that is equal to 625. Then we subtracted 625 from this equation number 1, and found out that according to equation number 1, 64r squared plus 288 and here 49 minus 625 equals to minus 576, that is equal to 0. So we have the quadratic equation that states that 64r squared plus 288r minus 576 equals to 0. We divided this equation number 1 by 32 and found out that 6r squared over 32 is 2r squared, 288r over 32 is 9r, and minus 576 over 42 equals to minus 18. So in conclusion, we found out that we have the quadratic equation 2r squared plus 9r minus 18 equals to 0, of course. This is the quadratic equation that we have. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18, and the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general solution for a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here x equals to r, so we substitute x by r, and we get that r equals to minus b. B equals to 9, so minus b is minus 9 plus minus b squared. B is 9, so b squared is 9 squared, it is 81. Minus 4 times a is 2, so it is minus 4 times 2, times c, that is minus 18. Divided by 2a. A is 2, so 2a is 2 times 2, that is 4. So in conclusion, we found out that r equals to minus 9 plus minus. Here, minus 18 times 2 is minus 36, and minus 36 times minus 4 is plus 144. So inside the brackets, inside the root, what is left is only 144 plus 81, all divided by 4. So r equals to 9 plus minus 81 plus 144 is 225. So inside the root, what is left is only 225, all divided by 4. So r equals to 9 plus minus, the square root of 225 is 15, all divided by 4. So here, you will have two solutions that are possible for r. The first solution for r is r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, but because of the fact that r is defined as the radius of this small circle, it's the length of the radius of the small circle, so r is a length, and as a length, it must be a positive number. It can never be equal to minus 6, that is a negative number. So we cancel this solution, we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4, so r equals to 6 over 4. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r equals to either 3 over 2 units, or we can represent it also as 1.5 units. Here, r, the radius of this small circle, it is equal to either 3 over 2 units, or we can represent it also as 1.5 units. Okay? Thank you very much.